Hello, friends. I hope it's a beautiful afternoon wherever you are. And IBM is here to give you yet another episode of Learning Physics. This is, remember, Physics 970. It's Physics 9702. So if you are not doing this physics, maybe you could be in the wrong class. However, it's nevertheless will be still useful to any person doing physics because the concepts somehow remain the same. In our previous lesson, that was temperature lesson 1, I guess we stopped on this reading assignment. I told you to read about the practical thermometers. These are basically the thermocouple, the thermistor, the liquid in glass thermometer. And I expected you to try and compare them in terms of range. You were supposed to look at the range. Also look at the sensitivity, compare the sensitivities of those thermometers and then know which one is suitable for what. So I expect that you have read about those practical thermometers. Some of them have been given in the notes, some information about them, but another more information could be found online or in the textbooks. So today I want us to move straight to lesson number temperature lesson number 2. Temperature lesson number 2 or lesson 2. So in lesson number 2, we shall actually concentrate more on the thermal properties of materials, and later on we shall see specific heat capacity in details. So in this lesson, we shall begin this with what we studied in IGCSE. We saw that every material is either a solid or a liquid or a gas, but scientists, as we saw earlier on, have developed a simple model which we call the kinetic theory to explain how solids, liquids, or gases behave. Or to be specific, scientists have come up with a simple description of how the molecules of solids, liquids, and gases behave. And according to the kinetic theory that we have already seen in the previous units, the previous parts, matter is made up of these tiny particles or molecules, and we saw from the kinetic theory that these molecules or particles or atoms are in constant random motion or are in continuous random motion as given by Brownian's experiment. The particles in some of these states attract each other, but the attractions weaken as the particles move far away from each other. And we saw that if we look at the solids, for example, the particles are very close to each other. Therefore, the interatomic or intermolecular or interparticle or interparticular forces are actually very strong in solids. But as we move down to liquids and gases, the particles are moving further and further apart. Therefore, the force of attraction between these particles tend to weaken, and the force becomes extremely weak when we talk about the gases. So every material is any of these three. It is either a solid, a liquid, or a gas. And the molecules making up these three states of matter have specific arrangements. We notice that in solids, the atoms or the particles are arranged in some kind of a regular pattern. This regular pattern, we have already called it lattice in some of the lower levels. So here atoms are arranged in a specific or in a regular pattern, as you could see, that is in solids. In liquids, the arrangement is relatively irregular, but the particles are still close to each other. Comparing the force of attraction between the particles of solids or the molecules of solids with the molecules or particles which make up liquids, we notice that the force of attraction in solids or between molecules, the so-called intermolecular force between molecules of solids should be far greater than the intermolecular force of attraction between molecules of solids. As we move to gases, we can see that the molecules are relatively far from each other, and therefore we know that the molecules of gases experience weaker forces of either attraction or repulsion between them. When I explain these three states in terms of the arrangement and the movement of molecules, then I'm relying on the kinetic theory of matter to explain these three states of matter. So, the distinguishing properties of solids, liquids, and gases are normally summarized by looking at one, their arrangement, and two, their movement, and maybe three, the forces or the strength or the nature of the force between these molecules. And this can be actually summarized on the next page. These are some of the distinguishing properties of the states of matter. I know you have already experienced this, you already know this, so I'm just rushing through it. So this table is going to try and summarize the most common properties of gases, liquids, and solids. And it helps to identify the molecular behavior responsible for each property. Let's begin with the gases. We know first of all that gases, the molecules, a gas assumes the shape and volume of its container. That's why we say gases do not have a definite shape or volume. A gas just takes up the shape and volume of its container. In fact, it fills up all the available space in the container. That's why when you are cooking, for those who know how to cook and you're using gas, you may not see a warning that the gas has remained halfway, because the molecules that remain within the cylinder tend to fill up the whole cylinder. So we say gases do not have shape, do not have volume, but they simply take up the shape and volume of the entire container in which they are placed. Number two, in comparison with the liquid, liquids also assume the shape of the part of the container which they occupy. When you pour water in a cup and it is half full, still the water takes up the shape of the cup up to that level where it is filled. So liquids also do not have a definite shape. They take up the shape of the container. Fortunately, liquids take up the shape of the container and attain what we call a definite volume. Unlike gases, where the molecules tend to fill up the whole container, for liquids, they attain a definite volume. So liquids have a definite volume. In liquids still, particles move, or particles can slide past one another. That's why when you pour water on a table or on the floor, it tends to spread all over, because the molecules can easily and freely slide past one another. When we compare with the solids, solids have a fixed volume and a fixed shape. They say they have a property which we call the rigidity. Rigid particles are locked into place. They are actually arranged into specific regular patterns that we called lattice. So, in solids, unlike liquids and gases, a solid has a fixed volume and it has a fixed shape. Solids have their particles locked into place. They are fixed into position. We have already seen that their vibrations, the vibration of these molecules or particles which make up a solid, are restricted to their equilibrium position. And that's why we said solids have a property that we called rigidity. Another distinguishing property that we can talk about is compressibility. Gases can easily be compressed simply because the molecules of gases are far from each other. That means there is a lot of space between the molecules of a gas. Similarly, it may not be easy to compress liquids because there is very little space or little free space between the particles. Unlike gases, where there is a large amount of space between the particles, for liquids there is very little space between the particles, is relatively hard to compress a liquid. If you want to experiment this, you can try to pour a liquid in a container which has a cover, then you try to push the cover inwards, or you can try to get a syringe, put there some water, then cover one end of the syringe and try to push the piston. You realize that it is very hard to compress a liquid as compared to compressing a gas, because for a gas there is a lot of free space between its particles compared to the liquid. On the other hand, it is impossible, let me say it is almost impossible to compress a solid. There is almost no free space between the particles that make up a solid. So that's why it is very, 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 very hard to compress a solid material, because there is almost no free space between the atoms or the molecules that make up the solid. Number three, we can talk about movement. We can talk about movement. We know that because there is enough free space between the molecules also move in gases. They are free to move past one another randomly with very high speeds. That's why sometimes we easily say that gases can easily flow. On the other hand, there is some little space between the molecules that make up liquids. Therefore, liquids have their particles sliding past one another. So particles in liquids can also slide past each other, can also move around each other, but not as particles in gases. On the other hand, uh, particles or molecules or atoms in solids cannot move from one point to another point, but we said their motion is restricted to vibration about their equilibrium position. So that means the molecules or particles or solid atoms of solids do not flow easily because they are interlocked into one another. They are actually fixed into place. They are only able to vibrate about their equilibrium position. So in conclusion, we have already seen that in terms of arrangement, particles of solids are tightly packed and arranged in regular patterns which we have called lattice. In terms of motion, particles of solids simply vibrate about their equilibrium position. Thus, they do not move from one place to another place. The only point which could be missing here is in terms of forces between them. The force between particles or molecules which make up solids, the force is very strong. In other words, the intermolecular force is very strong for solids. That's why their motion is restricted to vibration about their equilibrium position. On the other hand, when we talk about liquids, in liquids, molecules have an irregular pattern, or call it an irregular arrangement. We have already seen that in the previous page. The particles are relatively loosely packed and attract each other, but they vibrate so vigorously that attractions cannot hold them in fixed positions, and they slide past each other. So the particles are relatively loose, they are relatively loosely packed and close to each other. However, the force of attraction between these molecules is not strong enough to hold them into fixed position as it is with the solids. So for them, they can easily slide past each other. They can easily overcome the force of attraction because they vibrate vigorously, breaking the force of attraction so that they can slide past each other. So that is in terms of the force. And motion, of course. So in terms of motion, the molecules move randomly throughout the liquid, hence liquids can easily flow. I've explained this and I said normally when you pour a liquid on a table or on any surface, you see the liquid spreading on the surface. The molecules can easily slide past each other, therefore they can move randomly. That's why we say that a liquid is the flows. And number three, talking about the gas or the gases. In the gases, we already know particles are far apart. They vibrate, they move freely at very high speeds. So gases, as we have already mentioned, they will spread out to fill up the container. Of course, we have already seen that they exert pressure on all surfaces. They exert pressure on all surfaces of the container in which they occupy. So you should be able to explain the three states of matter, solids, liquids, gases, relying on the kinetic theory, but in particular focusing on number one, the arrangement of molecules or arrangement of particles. Number two, uh, number two is the movement of molecules. And number three, the force between the molecules or the particles. So you should be able to explain the three states of matter relying on to those three these three what? These three criteria. Okay, next let's talk about a simple explanation that will lead us to the latent heats. In one of the lessons, you were supposed to explain something relating to latent heats, and some people failed to explain what we mean by latent heat of fusion and latent heat of vaporization. Some of us were unable to explain why the latent heat of fusion is smaller than the latent heat of vaporization in terms of quantities. So we are going to start with a simple introduction. Let's begin with heating a solid. I'll consider the simplest solid. This could be ice. So imagine we are heating a solid. So we are beginning with a solid. Let's imagine we are starting with heating a solid. We are heating a solid. Imagine we are starting our experiment by heating a solid. Number one, we know that a solid is made up of molecules or atoms. These have definite equilibrium positions, but vibrating above these equilibrium positions with kinetic energy that depends on temperature. Remember, temperature is the average kinetic energy of the molecules that make up the system. So we are heating our solid. Because we have applied heat to the solid, what actually happens? At a certain temperature, we see the solid starts melting. So as we continue heating up to what we are going to call the melting point, we are heating up to what we are going to call the melting point. That is at the temperature at which a solid starts turning into a liquid. So as we heat towards the melting point, that means the solid is going to start turning into a liquid. That is at melting point. We are going to observe that the energy we are supplying at this point when the solid starts melting does not cause any change in temperature. So we are going to see that at melting, when the solid starts melting, the temperature remains constant. The question would be, where is the heat that we are continuing to supply going if the temperature is remaining constant? If the temperature is remaining constant, this is telling us that the average kinetic energy of the molecules is remaining constant, simply because temperature is the average kinetic energy of all of the molecules that make up the system. So if the temperature is remaining constant, where is the heat being supplied going at the point when melting starts? So it means this heat, remember, by conservation of energy, will not just disappear. It is going somewhere. Since it is not increasing the temperature, it should be doing something else. So instead, the energy which is being supplied is used to overcome the forces between the atoms and molecules. So during melting, the energy which is being supplied is no longer increasing the temperature, meaning it is no longer increasing or changing the average kinetic energy of the molecules. But by conservation of energy, that heat being supplied does not just disappear. It must end into the system somewhere. So this heat is going to overcome the force of attraction between the molecules. It is going to break the bonds. It is going to supply energy to break the bonds between the molecules. That is to overcome the forces between the molecules and the molecules. So that means there is some work being done. Work is being done, and since work is being done, then we say the potential energy of the molecules has actually increased. So potential energy of the molecules increases. So remember, the change in internal energy is equal to the random distribution of the kinetic and the potential energy of the molecules. Since the temperature is remaining constant, it means the average kinetic energy is remaining constant, which means the total kinetic energy is remaining constant. But energy is being supplied, heat is being supplied. So this heat supplied must be somewhere. And we are saying the heat supplied, although it doesn't change the temperature, the heat supplied goes into overcoming the force between the molecules, that is, breaking the bonds. Therefore, some work is done as the molecules are pushed further apart from each other. Therefore, the potential energy contribution is the one which increases as this remains constant. Because the potential energy contribution increases, it means the internal energy increases even when the kinetic energy of the molecules is not increasing. So the heat we have supplied, which has not caused any physical effect that we can see. Of course, here the physical effect we can see with our naked eyes would be a rise in temperature. Since the temperature is not changing, even if I place there the thermometer for long, the temperature will not be seen to be changing. So it means we can't see this physically, but there is still, it doesn't mean the energy is being just wasted or disappearing through thin air. So this heat, whose effect cannot be seen with with any physical observation in the environment, is what we are calling, or what we are going to call, the latent. We are going to call this the latent heat. The word latent means concealed. The word latent means concealed. In a layman's language, this would mean hidden. So the heat is, it's like its effect is concealed. We can't see it physically, but it doesn't mean it's just wasted. To be specific, when we are moving from a solid to a liquid, that is when there is melting, that is the changes from solid to a liquid, we shall specifically call this one the latent heat of fusion. From solid to liquid, we shall call it the latent heat of fusion. So when a solid changes to a liquid, that heat is going to be called the latent heat of fusion. Okay, so when someone talks about latent heat, there is no change in temperature. The amount of heat which is required to change the state of a substance without a change in temperature is what we are going to call the latent heat. So for latent heat, there is change of state without change in temperature. There is change of state without change of state without change in temperature. That is what we mean by latent heat. That amount of heat which is required to change the state of a substance without change in temperature. Amount of heat required to change the state of a substance without change in temperature. We are saying if we are changing from a solid to a liquid, it will be called the latent heat of fusion. That amount of heat required to change a solid to a liquid is what we call the latent heat of fusion. But remember, there should be no change in temperature. Changing a solid to a liquid without change in temperature is going to be called latent heat of fusion. That amount of heat required to change a solid into a liquid without change in temperature, that amount of heat required to change a solid into a liquid at constant temperature is what we are going to call the latent heat of fusion. So um, fusion relates to solid to liquid. Then, on the other hand, remember we have started heating and we have moved from solid to liquid. Let's now continue heating again from liquid to gas. We are continuing our heating. We are continuing our heating from liquid to gas. But before we continue heating, I want you to note that as heating continues, the atoms can now move about each other relatively freely in the liquid phase because we are now turning to liquid. But still, they are still close enough to experience interatomic forces. They are still close to each other, so they can still experience interatomic forces. And we have said they still have potential energy, which is associated with these forces, uh, the corresponding, as well as kinetic energy correspond to the rise in temperature. So after all the liquid has melted, we are now heating. Initially, the molecules are still close to each other, so they experience intermolecular forces. But since the forces still exist, we say there is potential energy because of these forces. However, since the solid has melted and is now a liquid, the temperature again suddenly starts increasing, meaning that at this point, the total kinetic energy of molecules starts increasing, the average kinetic energy of molecules starts increasing. That's why now we see the temperature rising. So between a liquid to gas, before it starts turning to a gas, the temperature starts rising when all the solid has become a liquid. The forces between the molecules have been broken, but their separation of or the separation of the molecules has not increased significantly when we move from solid to liquid. That's why I am saying there still exists some interatomic forces when a substance or when a solid becomes a liquid. And we have already seen earlier on that a liquid has a fixed volume, even though it has no fixed shape, but takes up the shape of the containing vessel. And some liquids, some solids, when they melt, the density of the solid is almost the same as the density of the liquid that is formed. So for some substances, the density does not change significantly. But then, when the liquid starts turning to a gas, remember we have been supplying heat all along and the temperature has been increasing from liquid or when it had become a liquid. So at a certain temperature that we shall call the boiling point, this one we call it the melting point. At a certain temperature, which we shall call the boiling point, the temperature at which now a liquid is going to, or a liquid uh, is turning into a gas completely at a certain temperature called the boiling point, the atoms now start escaping into the gaseous phase or the gaseous state. Here now the interatomic forces in the liquid must be overcome completely. The interatomic forces between the molecules in a liquid, for it to move to the gaseous phase, they must be broken completely. The energy we put in here is therefore going to be called the latent heat of vaporization. So what is happening here? We are now moving from liquid liquid to gas or liquid state to gaseous state. So the molecules were still experiencing some weak force when we were in the liquid state. But if the molecules are to escape the gaseous phase, the interatomic or the intermolecular forces have to be completely broken so that the molecules are completely far from each other and completely free. So this goes into moving the molecules. The heat supplied will go into moving the molecules far enough apart for the interatomic forces and hence their associated energy or potential energy to be negligible. One of the assumptions of the kinetic theory is that for an ideal gas, there are no forces between atoms or molecules because the forces are actually negligible. That's why we say the interatomic force, the potential energy due to the forces is going to be negligible. So when we are moving from liquid to gas, the molecules must move infinitely far from each other so that they do not experience or the intermolecular force is extremely weak and almost negligible. So the heat we are supplying here is going to be called the latent heat of vaporization. Remember, when a liquid starts boiling or when a liquid starts changing into a gas, still the temperature remains constant. That's why the word latent still comes back. There is a change of state, there is a change of phase, still the temperature remains constant. But at this point, the heat we are supplying, which we are calling the latent heat of vaporization, is no longer going to change the temperature when the boiling starts. If the liquid is water and boiling is occurring at 100 degrees Celsius, you may realize that the temperature may never change from 100 degrees Celsius. It may remain 100 degrees Celsius throughout, as long as the liquid is changing to gas. So that's why we are still calling it latent heat. There is no change in temperature, but there is a change of state from liquid to gas, giving it the name latent heat of vaporization. So that amount of heat required to change a liquid to a gas without changing temperature is going to be called the latent heat of vaporization. That amount of heat required to change a liquid into a gas at constant temperature is what we are going to call the latent heat of vaporization. So now we know the meaning of the word latent. Latent is going to mean hidden or concealed. It is said to be hidden or concealed because there is no temperature change. We can't see temperature changing, but all we could see is that there is a change of state. So a change of state is happening when the temperature is remaining constant. One important thing we need to note is that we can now predict easily that the latent heat of vaporization, which is normally given as LV, is going to be greater than the latent heat of fusion, which is normally going to be denoted as LF. Why? When melting occurs, the change in volume is relatively small. When a solid melts, the change in volume is relatively small. You can always experiment this with ice. When a block of ice melts, the change in volume is relatively small. And remember, work done is equal to pressure times change in volume. If the change in volume is relatively small, it means that the work done is also going to be relatively small. So during melting, little amount of work is done to push the molecules slightly far from each other, that is, in liquids. So since little work is to be done, little amount of energy is also required. For during vaporization, when a liquid is changing to a gas, the change in volume involved here is very large. There is a large change in volume. That means the work done is also going to be large if there is a large change in volume, simply because a lot of energy is required to do work against the atmosphere as molecules escape the liquid state to the gaseous state. If this is a liquid which is boiling, the molecules trying to escape here have to push against the atmosphere So a lot of work is done to push against the atmosphere as these molecules escape the liquid state into the gaseous state. Because a lot of work is done, it means also a lot of energy is going to be required. For this reason, the latent heat of vaporization will always be greater than the latent heat of fusion. The energy required to completely separate the molecules is greater than the energy required to simply break the bonds in the solids. So in the liquid to gas, energy is required to completely separate the molecules. Yet from solid to liquid, energy is just required to break the bonds. Furthermore, energy must be provided to push back the atmosphere as the liquid turns to vapor. Note that the volume of vapor is going to be much greater than the volume of the liquid. The volume of vapor is going to be much greater than the volume of the liquid. So it implies the volume change during vaporization is far greater than the volume change during melting. And since work done is directly proportional to the change in volume, more work is done during vaporization than during melting. I think I've tried to explain that further in details. So, note number one, we know that melting occurs at a constant temperature. If it is ice, most likely at 0 degrees Celsius. At the same time, boiling also occurs at a particular temperature. If it's pure water, I think boiling occurs at 100 degrees Celsius. Note that we have associated boiling and melting with a definite input in energy, only that input in energy does not show any physical effect. That's why we say this energy we are putting in is going to be called the latent heat. The energy we are putting in is going to be called the latent heat. However, molecules are going to be lost from the surface of a liquid at any temperature, even when we don't apply any heat. Now this brings in the concept of evaporation. Molecules are going to be lost from the surface of a liquid even when we don't apply any heat. This brings in the concept of evaporation that we are going to see shortly. Let's first have a simple outline of the points we need to or we must have noted from this part. Number one, we have seen that the word latent means hidden or concealed. We have also said fusion is for solid to liquid, vaporization is for liquid to gas. Latent heat of vaporization is much greater than latent heat of fusion because one, vaporization involves a much greater volume change than fusion, meaning much energy must be provided to push the atmosphere. Actually, this is to push back the atmosphere as the liquid turns to vapor. So the energy required to completely separate for vaporization, energy is required to completely separate the atoms, which makes it much greater than the energy required to simply break the bonds that is in the solid. So solid to liquid, energy is most likely required to simply break the bonds because the molecules will still stay close to each other. Then liquid to gas, energy is required to completely break the bonds that the one molecule does not experience any force due to a neighboring molecule. This means vaporization will require much more energy than fusion. So note very well, you should be able to define latent heat. Energy required to change the state of a substance without change in temperature. If it is latent heat of fusion, the energy is required to change a solid to a liquid without change in temperature. If it's latent heat of vaporization, the energy is required to change a liquid to a gas or vapor without change in temperature. Later on, we shall add the word specific. For example, we shall see specific latent heat of fusion and specific latent heat of vaporization. When we add specific, now we shall specify that a mass of 1 kilogram is considered. Here we are still general. Energy required to change the state of a substance without changing temperature, that is the latent heat. If it is specific latent heat, then we shall specify the mass of 1 kilogram of that particular substance. Okay, for now, let's first explore evaporation, because we have seen that even when there is no heat supplied, molecules can still be lost from the surface of a liquid. At any temperature, molecules can be lost from the surface of the liquid. Note very carefully that temperature is equal to the average kinetic energy of the molecules. I am saying at any temperature, molecules can be lost from the surface of a liquid. By the kinetic theory, the molecules in a liquid do not all move with the same speed. They actually move randomly, therefore they have a wide distribution of speeds. A molecule with a high enough speed may easily escape from the attractive force of the molecules in the surface region of the liquid and leave the liquid entirely. This process can occur at any temperature. So if we have a container which is containing a liquid, let's have a vessel with a liquid. There are those molecules which are just on the surface so that they can easily escape the surrounding. These molecules should be having high enough kinetic energy, they should be having high enough speed or high enough energy to break free from the attraction of all the other molecules within the bulk of the liquid. So, a molecule close to the surface with high enough kinetic energy is bound to escape from the liquid, to break free from the liquid and escape. By the way, this can occur at any temperature. But if we increase the temperature of the liquid, what does that mean? It means a great number of molecules within the liquid will be moving very fast. Increasing the temperature of the liquid means we have increased the average kinetic energy of the molecules that make up the liquid. This implies we have increased the total kinetic energy of the molecules that make up the liquid. And therefore, the molecules on the surface have a high enough energy to break free. But then, what happens to the liquid which remains behind if we are not increasing the temperature? So, the higher the temperature, the greater the number of fast-moving molecules, and therefore the greater the loss of molecules from the surface. I think this proves our daily observation that evaporation rate increases with an increase in temperature of the surroundings. And the loss of the fastest molecules means that the average speed of those that are remaining, therefore the average kinetic energy of those that are remaining is also reducing, which means with the time, evaporation would cause cooling. With the time, evaporation would cause cooling. I think this too is an everyday observation that evaporation causes cooling. Sometimes when you sweat, you realize that your body cools down. So we are saying number one, evaporation occurs constantly at all temperatures. Unlike melting and boiling which occur at specific temperatures, evaporation can occur at any temperature. Number two, we are saying that there are those molecules which are more energetic, those with the highest kinetic energies, very close to the surface. Actually, it is the surface molecules which escape fast, because for them, they have only one side of them being attracted or being exposed to other forces. But above them, there is no serious force, therefore they can easily escape the atmosphere. So it is the surface molecules which are more energetic that can easily escape and become gas molecules. Note that temperature is determined by the average kinetic energy of the liquid molecules. Now, what happens? When the more energetic molecules escape during the process of evaporation, the average speed, therefore the average kinetic energy of the molecules left behind decreases. Thus, the temperature decreases, therefore the liquid cools down as evaporating goes on. The question we are trying to explain here is that why does evaporation cause cooling? Why does evaporation cause a decrease in temperature? To begin with, temperature is the average kinetic energy of the molecules that make up the system. When the more energetic molecules escape and leave the liquid, it means the average speed and therefore the average kinetic energy of the molecules has reduced for those which have remained behind, because those with the highest speeds or highest kinetic energies have moved out. Those which are remaining must be having smaller kinetic energies. So if the average kinetic energy of the molecules reduces, it simply means the temperature should therefore decrease. Therefore, we say that evaporation will cause cooling. And here there is a simple everyday experience. You must have experienced that sweating cools your body. And it's because sweat absorbs more energy from your skin so that it can continue to evaporate. So every time you sweat, your body cools down. The reason is because as you sweat, the sweat itself absorbs again more energy or more heat from your body so that the body continues to evaporate and you cool down. So we are saying evaporation causes cooling because temperature is the average kinetic energy of the molecules that make up the system. As the more energetic molecules on the surface leave the liquid, only the less energetic molecules are the ones left behind. That means the total kinetic energy of the molecules remaining behind is smaller, which means the average kinetic energy of the molecules remaining behind has reduced. Therefore, the temperature has reduced. Since temperature is the average kinetic energy of the molecules that make up the system. I think you deserve a self-check at this point. Self-check number one. Self-check number one. Self-check number one. No, you have not yet arrived at the self-check. Maybe I can first leave you for now. Okay, before we go to the self-check, let's go to the summary of the distinguishing of the factors which influence evaporation. So we have seen evaporation, and some of the factors which influence evaporation, we have mentioned them in IGCSE. These factors could be very important in paper 5, planning an experiment. Temperature is one of the factors which influence evaporation. We have already seen that when we heat or we increase the temperature, it means the average kinetic energy of the molecules is increasing. Total kinetic energy of the molecules on the surface increase. That means more molecules escape because they will have high enough kinetic energy to escape from the liquid. So temperature increases evaporation as more particles have sufficient kinetic energy to escape from the surface. Wet clothes dry faster on a warm day because the particles, that is water molecules, have enough energy to escape. I think that is an everyday observation or experience. On a warm day, wet clothes dry faster than on a cool day or a cold day. So temperature increases evaporation. Number two is surface area. I think this is an everyday experience too. If you pour your porridge if you have porridge on a plate and an equal amount of porridge in a cup, you realize that after a short period of time, porridge on a plate will have cooled faster than porridge in a plate, simply because surface area somehow means that uh, a high surface area means that more molecules are exposed to the atmosphere, therefore they can easily escape. So the molecules of the porridge on the plate will cool faster, since we have seen evaporation causes cooling or results into a decrease in temperature. The porridge on the plate will cool faster because more molecules are exposed to the surrounding. Therefore, more molecules can easily escape the surrounding as compared to that porridge which is in the cup. So, the higher the surface area, the higher the rate of evaporation. So, surface area affects evaporation. And lastly is drought. Drought or wind and dryness of air. This one we also experience it in our everyday life. Many times when you are drinking your porridge during breakfast, you tend to blow air above the cup. That is a common practice with everyone when we're growing up, of course. When you are drinking porridge, you tend to blow air above the cup, and you realize with the time that the porridge tends to cool down very fast. So air currents moving over the surface of a liquid increases the rate of evaporation, because the air current blows away the vapor molecules which have already escaped before they return to the liquid. So when you blow air above the cup, you are blowing away the vapor or the vapor molecules which have already escaped from the liquid or from the porridge, so that you give room for more molecules to continue escaping from the liquid. That's what we mean by creating a drought. That is creating a drought. So this is the reason as to why wet clothes will dry faster on a windy day than on a normal day. So when it is very windy, wet clothes can still dry faster, because um, the wind tends to blow away, it tends to blow away the molecules which have already left the clothes, so that more molecules can still leave the clothes. So that is what we are referring to as drought. Okay, so we have seen evaporation occurs at any temperature, and we mentioned that boiling or melting occurs at fixed temperature. Let's have a summary of the difference between boiling and evaporation. One, if you have ever boiled water, you will realize that boiling occurs in the bulk of the whole liquid, but evaporation takes place only at the surface of the liquid. It's only those molecules which are exposed to the surface which can easily escape, because there are unbalanced forces acting on them. Unlike molecules in the bulk of the liquid, where there are forces surrounding them in all directions. So boiling occurs in the bulk, that is throughout the liquid. So when I say in the bulk, I mean throughout the liquid. Yet evaporation only takes place at the surface. Number two, boiling occurs at a fixed temperature, yet evaporation takes place at any temperature. We can experience evaporation at any temperature or at all temperatures. Once boiling takes place, the temperature of the liquid remains constant. This almost reinforces the other one, that once boiling takes place, the temperature is constant. That is, boiling takes place at a constant temperature or at a fixed temperature. Of course, boiling does not cause cooling. But once evaporation takes place, there is a fall or a decrease in temperature. That's why we said evaporation causes cooling. If you have observed a liquid boiling, you must have seen that boiling is rapid and a noisy process, but you may not actually realize that a liquid is evaporating, because evaporation is a slow and calm process. This one, we experience it in everyday life. If you haven't experienced it, just put water on fire just now until it starts boiling. You realize that when boiling is occurring, it is quite noisy and rapid. Then after boiling the water, now put it aside so that it cools down. you realize that you will not even notice that it's cooling down because evaporation is a slow and calm process. Okay, I think we now qualify for self-check. Self-check number one. Self-check number one. From all that we have just discussed, you should now be able to explain using the simple kinetic model why boiling and melting take place without a change in temperature. Number two, you should explain still using the kinetic model why the specific latent of vaporization is higher than the specific latent of fusion for the same substance. You can think about ice or ice and water because it is almost the same substance. Number three, explain using the simple kinetic model still why a cooling effect accompanies evaporation. In other words, explain why evaporation causes cooling. I think you should be able to, to do that self-check. Okay, let us move to another not very important but um, concept, and this will be atomic spacing. In in AS, we talked about the scale of things, especially in particle physics. At that point, we were just quoting that actually the interatomic spacing was verified to be approximately 10 power negative 10 meters, I think, which was almost the same as the diameter of an atom or the size of an atom. But then the question would be, how does it come to such values? So according to the simple kinetic model of matter, we can estimate the spacing of atoms or molecules for a solid uh, using known values of density. We can estimate the spacing between atoms or molecules which make up a solid using or relying on known values of its density and the mass containing one mole, that is the molar mass. If I know the molar mass and I know the density of the substance or the solid, I can always estimate the spacing, just an estimate, the spacing between the atoms which make up such a solid. Surprisingly, each time you do a calculation, you'll find that the number or the order 10 power negative 10 meters will come up for a solid. Every time the order or the number 10 power negative 10 meters will come up every time you do a calculation relying on the density and the mass or the molar mass of that solid. Therefore, we simply say that the order of magnitude of the spacing of atoms in a solid is 10 power negative 10 meters. The order of magnitude of the spacing of atoms in a solid is 10 power negative 10 meters. For liquids, because the molecules are slightly far from each other, slightly, the average spacing of the atoms is sometimes twice. It is up to twice that in solids. Of course, it means the order is still the same. It is just twice. So it means the power of 10 is still the same. The interatomic spacing between solids and liquids is of the same order. But for gases, the average spacing is almost of the order 10 power negative 9 meters. You can say how many times compared to the solid and liquid. So this is what we call the scale of things in AS particle physics. But we can try to see how possible is it that every time we carry out a calculation relying on the density of the substance and the molar mass, we come up with an atomic spacing of almost the same order as 10 power negative 10 meters. 10 power negative 10 meters. What has happened to my pen? Let's say a simple example. Assume that atoms in iron are arranged in a simple cubic lattice as shown below. So let me show this. Let me draw a simple cubic lattice. let us assume that the atoms, I don't know whether that is a cube, but I've tried, I know. So let us assume that atoms are arranged in a simple cubic lattice. This is an ion, that is Fe5626. Estimate the spacing between the atoms in ion. The density of ion is this, and its molar mass is that. If the molar mass is known and the density of ion is known, then we can estimate the interatomic spacing. We can estimate the interatomic spacing. So how many moles do we expect to be in 1 meter cubed of 7,900 kilograms of iron? Note that 1 mole of a substance, let me start from here. 1 mole of a substance contains 6.02 times 10 power 23 atoms. This is Avogadro's number. This is Avogadro's constant, Na. So we have the density to be 7,900 kilograms per meter cubed, which means that 1 meter cubed of iron has a mass of 7,900 kilograms. I've just quoted it from here. A density of 7,900 kilograms per meter cubed means that in 1 meter cubed volume, the mass is 7,900 kilograms of iron. A volume of 1 meter cubed of iron has a mass of 7,900 kilograms. So it means, remember we have that 1 mole of this iron, 1 mole has this number of atoms, but the molar mass is 56 times 10 power negative 3 kilograms. And how many moles are these? How many moles are these? So we said number of moles is going to be equal to the mass divided by the molar mass, which will simply be 7,900 divided by the molar mass, which is 56 times 10 power negative 3. Alternatively, you can do it locally. You say, okay, if 1 mole has this number of atoms, if 1 mole has that number of atoms, and 1 mole is actually this mass. If this is the molar mass, then 1 mole has this mass. So this mass contains this number of atoms. How about this mass? So you can do that manually. But when I do this, calculator, 7,900 divided by 56 exponent negative 3. So this is giving me 1.4 times 10 power 5 moles. So that is the number of moles. That is the number of moles. But remember, 1 mole has this number of atoms. So how many atoms are these? So the number of atoms, since 1 mole has this number of atoms, the number of atoms I have in iron will therefore be 1.4 times 10 power 5, then times 6.02 times 10 power 23. So I just multiply this. So this is giving me 8.428 times 10 power 28 atoms. So this is the number of atoms that I have. But remember, I'm looking for interatomic spacing. So if I make an assumption that these atoms are arranged in a regular cubic lattice as mentioned, along one side of the 1 meter cube, let's think of these atoms being arranged just on one side of a 1 meter cube. That means on just one side, that is on one side of the cube, I am most likely going to have the cube root of this as the number of atoms, because all these atoms are in 3 dimensions, are arranged in a 3-dimensional cube. Now, if I want only one side of the cube, then most likely I'm going to get the cube root of this value. So on one side, the number of atoms is going to be equal to the cube root of 8, the cube root of 8, 8.42, 8.428 times 10 power 28. And when I press my calculator, this is giving me 3. So this is giving me 4, not 3. So this is giving me 4.38 times 10 power 9 atoms. These ones are arranged on one side of the cube. But remember, one side of the cube has a length of 1 meter. One side of the cube has a length of 1 meter because this is a cube, 1 meter, 1 meter, 1 meter, and so on. So it means the interatomic spacing is therefore going to be equal to 1 divided by, because one side of the cube is 1 meter, so the interatomic spacing is going to be equal to 1 over 4.38 times 10 power 9. And when I divide this, so this is 2.3 times 10 power negative 10 meters. Already the power of 10 has come out to be 10 power negative 10. So now, because we made an assumption about the simple cubic arrangement of atoms in iron, which is not in fact true. Not all the arrangements are in cubic. Not all the atoms are arranged in a cubical lattice. So that means the value we are giving here is an estimate. Therefore, I can't give this estimate to many significant figures as we saw in AS. So I can simply say that the interatomic spacing is approximately 2 or maybe 2.0 times 10 power negative 10 meters. Since it is just an estimate, I minimize the number of significant figures to which I quote this. So every time a calculation is taken to find the interatomic spacing relying on density and the molar mass, if the substance is a solid, it will result into an order of 10 power negative 10 meters. Similarly, if it is a liquid, the order will still be the same. For a gas, the order will be 10 power negative 9. Let's see if there's another example, maybe. Example number 2. Estimate the interatomic spacing in aluminium, for which the density is 2,700 kilograms per meters cubed and the molar mass is 27 grams. So we can make an assumption and say that the atoms are arranged in a simple cubic lattice. So without wasting any time, we know that 1 mole contains 6.02 times 10 power 23 atoms. Let's find the number of moles first. Number of moles is going to be mass divided by the molar mass, which will be mass is 27 grams. So this will be 27 I'm changing it to kilograms times 10 power negative 3 divided by the molar mass. Sorry. This is the molar mass actually. So the mass will be got from here. In 1 meter cubed, the mass is 2,700 kilograms. So this will be 2,700 kilograms divided by the molar mass, which is 27. To change it to kilograms, is times 10 power negative 3. So that is going to be the number of moles. Remember, 1 mole has 6.02 times 10 power 23 atoms. So it means the number of atoms is going to be equal to the number of moles, 2,700, divided by 27 times 10 power negative 3 times 6.02 times 10 power 23 atoms. When I press my calculator, you can also press yours and see. So this is giving me a 6. So this is 6.0 times 10 power 6.02 times 10 power 28 atoms. So the number of atoms that we have is 6.02 times 10 power 28 atoms. Then remember we said we have assumed the atoms are arranged in a cubic lattice, in a regular cubic lattice. Therefore, just on one side of the cube, on one side, we are finding the estimated number of atoms on one side. On one side, the number of atoms will be the cube root of 6.02 times 10 power 28. And when you press your calculator, so this is approximately 3.9 times 10 power 9 atoms. On one side of the cube, we approximately find that the number of atoms is approximately 3.9 times 10 power 9 atoms. But remember, a cube is 1 meter cubed. A cube is 1 meter. One side of the cube is 1 meter. So it means the interatomic spacing is going to be equal to 1 over 3.9 times 10 power 9. And when I press my calculator, so I'm getting 2.5 times 10 power negative 10. But remember I said since we have just made assumption, we shall write this to one significant figure, 3 times 10 power negative 10 meters. So every time a calculation is carried out, the order of 10 power negative 10 meters always will come up as the interatomic spacing of a solid. If it is a liquid, the same order will come up. However, it will slightly be different. It will be 10 power negative 9 for a gas, because for a gas, the molecules are relatively farther apart compared to a liquid. Okay, so that is all about interatomic spacing. Let's move to the specific heat capacity. Specific heat capacity. Specific heat capacity. I think this is a concept that we studied in IGCSE. So we have earlier on seen that when a solid is heated at a certain temperature, it starts melting. That is at melting point. And we said when it starts melting, the temperature remains constant. And we said the heat supplied was the latent heat. If we continue to heat the liquid, because the solid has already melted, now again the temperature starts increasing. When the liquid starts changing into a gas, then the temperature now remains constant. That is at boiling point. And we said this was the latent heat of vaporization. So when a solid, or a liquid, or a gas are heated, we expect the temperature to rise. If we were to plot a graph of thermal energy supplied against the temperature, as we apply more heat, if we have not reached a change of state, as we apply more heat, we expect the temperature to rise. So that if I sketch a graph of temperature, or if we were to plot a graph of thermal energy against temperature, so this is heat applied or thermal energy applied, heat supplied I'm plotting this against temperature. We expect this to be a perfect straight what? Expect this to be a perfect straight line. When a graph of thermal energy supplied against heat is plotted, we expect it to be a straight line. What does the straight line imply? The straight line implies that the amount of heat supplied, delta Q, should be directly proportional to the change in temperature, delta theta, as long as there is no change of state. Whether it is a solid, whether it is a liquid, whether it is a gas being heated, we expect a temperature rise as long as there is no change there is no change of state. So let that be our first equation. Here we have assumed that the mass of the substance being heated is constant. But then, suppose the heat energy, or suppose we want to cause the same temperature change. We want to cause the same temperature change. That means we must change the mass and change the amount of heat. Therefore, the heat required to produce a particular temperature rise must be proportional to the mass of the substance which is being heated. We want to cause the same temperature rise. Therefore, the amount of heat required to cause the same temperature rise must depend on the mass of the substance being heated. You can't apply the same amount of heat on half a cup of water as you would do to a full cup to cause the same temperature rise. So the amount of heat required to cause the same temperature rise will depend on the mass being heated if the temperature rise is constant. Therefore, if I was to sketch a graph of heat supplied or thermal energy supplied against mass, this will still be a straight line. This will still be a straight line. That is, delta Q is going to be directly proportional to the mass. This will still be a straight line. So this is going to be our second equation. So let's try to combine the first equation and the second equation. Delta Q is directly proportional to delta theta. Delta Q is still directly proportional to the mass. So it implies that delta Q is going to be equal to the mass times specific heat capacity times delta theta. So I have just introduced equal signs and a constant C that we have already seen from IGCSE. So because delta Q is directly proportional to delta theta, at the same time is directly proportional to the mass, delta Q is directly proportional to the mass and directly proportional to delta theta. So I simply introduce equal signs and a constant. The constant C is what we call specific heat capacity from IGCSE. The constant C, or the constant of proportionality, is what we call the specific heat capacity. The word specific now is going to be meaning or referring to per unit mass. So specific is going to be referring to per unit mass. So C is the specific heat capacity, and this is going to be referring to per unit mass. So the numerical value of specific capacity of a substance is actually that amount of heat which is required to raise the temperature of a unit mass of the substance by either 1 degree Celsius or by 1 Kelvin. That amount of heat required to raise the temperature, because we have seen as long as there is no change of state, there is a change in temperature. So the amount of heat required to change or to raise the temperature of a substance by 1 degree Celsius or by 1 Kelvin is going to be called the heat capacity. If the substance is actually 1 kilogram, that is per unit mass, then this will be called the specific heat capacity. Therefore, we shall define specific heat capacity of a material as the heat or amount of heat required to raise or to change the temperature of 1 kilogram of a substance by 1 Kelvin or by 1 degree Celsius. Those of you who remember, we said that change in temperature on the Kelvin scale is the same as a change in temperature on the degree Celsius or on the centigrade scale. Therefore, Therefore, I can say the amount of heat required to change or to increase or to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or by 1 Kelvin. So if I make C the subject from this expression here, I can establish the units of specific heat capacity. So C is going to be equal to delta Q divided by M delta theta. So if I consider only units, this will be joules divided by kilograms divided by, that is Kelvin. So this will be joules per kilogram per Kelvin. So those will be the units of the specific heat capacity. Those will be the SI units. Those will be the SI units. So some things that we need to note from this are very few. Number one, we have already established this equation right from IGCSE. So what does this equation tell us? First of all, the amount of heat required to raise the temperature or to change the temperature of 1 kilogram of a substance is what we call its specific heat capacity. When you make this C to be equal to Q divided by M delta theta, you notice that this is the most important relation. If we say that a material has a high specific heat capacity, if a material has a high specific heat capacity, that is a high value of C, what does that mean? It requires more energy to raise the same temperature for a material with low specific heat capacity. If a substance has a high specific heat capacity, then it means it requires more energy to cause the same temperature rise with a material, or for a material with low specific heat capacity. Let me give a simple example. If, for example, we have a liquid such as water, a liquid, and we have, let's say, sand. If we were to cause, for example, the temperature of water or the temperature of the sand to increase by just 2 degrees Celsius or by 1 degree Celsius each, we shall notice that we may require more energy to raise the temperature of water by 2 degrees Celsius as compared to raising the temperature of sand by 2 degrees Celsius. What does that imply? Water has high specific heat capacity compared to sand. So a material with a higher specific capacity will require more energy to raise its temperature for a given material. It will require more energy to raise its temperature as compared to that for a given material that has a lower specific capacity. It means it will not be easy to raise the temperature of water by 2 degrees Celsius. It will require more energy. But it will be easier, or it will require less energy to raise the temperature of sand by 2 degrees Celsius. So it's a sand whose temperature can easily be raised has a lower specific heat capacity. Water whose temperature cannot easily be raised, it requires more energy, therefore has a higher specific heat capacity. So materials like aluminium and copper have low specific capacity. Therefore, these materials are easily heated and easily cooled. That's why you see most saucepans at home are made out of copper, I think, and aluminium. So these ones have low specific heat capacities. So we can think about the term specific capacity of a substance to be something relating to what we call heat loving, maybe heat loving, affinity for heat, you know. Because later on we are going to see, if you have seen sea breeze and land breeze, you will notice that a material which requires more energy to gain heat will also not easily lose the heat. A material which takes more energy to gain the heat may not also easily lose the heat. It is heat loving, or it has high affinity for heat. So think of the sea breeze and land breeze. For those who have been to Gisenyi, you must have experienced sea breeze and land, or you must have an idea about the sea breeze and land breeze. During the day when it is too hot, when you stand beside the showers, you feel cool air blowing towards you. That's what we refer to as a sea breeze. The word breeze means wind in motion or wind moving. So when you stand just beside the showers, you feel a cool breeze blowing towards you. You feel cool wind blowing towards you, even when the sun is very bright. That's what we call a sea breeze. Why do we experience that? During the day, the land heats up faster than the sea. So during the day, the land heats up faster than the sea, and because the land heats up faster than the sea, if this is the sea, and the land heats up faster than the sea, and this is the land, so what happens during the day? There is more warm air above the land than the sea, so warm air is less dense, it rises up. When warm air rises up, it allows or it gives room for cool air to blow towards the land. This cool air from above the water is the one you feel blowing towards you when you are standing just here on the shores. So this is what we call a sea breeze. This is because land heats faster than the sea simply because soil has a smaller specific heat capacity. It requires a smaller amount of energy to raise its temperature compared to water. But again at night, the opposite happens. At night, the opposite happens. Let's assume this is the sea, or this is the ocean, and this is the land. At night, because water requires more energy to gain the heat, or to raise its temperature, it will also not easily lose its heat. Therefore, its temperature will not easily fall. Therefore, at night, again the land, which has a smaller specific capacity, cools faster. It heats faster during the day and cools faster during the night. So it means there will be now more warm air above the sea than the land. There will be therefore cool air at the land compared to the sea. Warm air which is above the land rises, giving room for cool air which is on the land to blow towards the sea. So even when you are above the water during the night, you still feel a cool breeze blowing from the land towards the water. So this is what we call a land breeze. So this is land to the water to the ocean, that is the land breeze, and this is from the water to the land, that is a sea breeze. So all these are relying on the specific heat capacity. Something with a lower specific capacity easily heats up, that is, requires small amount of energy to raise its temperature, and easily cools down, that is, it requires a small amount of, or it takes a small time to lose the energy which it has already gained. So that is specific heat capacity. I hope I've tried my level best to explain specific heat capacity in details. Okay, so let's see some of the methods that can be used to determine specific heat capacity. Methods used to determine the specific heat capacity. Let's begin with a solid. Um, the simplest way of determining the specific capacity of a solid is maybe using a cylindrical block of that solid, as shown here. Here I have a cylindrical block of the solid, or a solid which has been cut into a form of a cylinder. For you could be seeing rectangular, but me, I'm seeing a cylinder. So what is very important are these two holes drilled into this block. One hole is to insert a thermometer, because this will be used to measure temperature. Then another hole is going to be for the heater, because the heater is going to supply heat energy to the block. So as we supply heat, as early on we have seen, we expect that as long as there is no change in state, the temperature must be changing. What is very important is this part here where we have a voltmeter connected in parallel. Its work will be to tell the potential difference, so we shall need V. And we have an ammeter, its work will be to measure the current, so we shall need I. Here I have a variable resistor, so I may have several values of I and V. And the switch, a low voltage supply. So because I am going to measure the specific heat capacity of a substance, in my mind, I know that amount of heat supplied is equal to mc delta theta. So it means I need the amount of heat supplied. I need the mass. I need to measure or determine the temperature difference to be able to find the specific heat capacity. So number one, I will measure the mass of the metal block. So I need the mass m. I will measure the mass of the metal block m. Of course, to measure the mass, this will be done using a beam balance. Any balance to measure the mass. Then, of course, I'll place this into an insulation or a lagging material to minimize heat losses to the surrounding. So a low voltage, here I have a low voltage heater and a thermometer which have been inserted in two holes that have been drilled in this solid. So number one, I will measure the temperature Ti. Measure the temperature Ti, I'll call this temperature Ti. Initial temperature of the solid before switching on the heater. Switch on the heater, I will of course close the switch. Then of course I measure at a constant voltage and a constant current. That means I will note values of I will note constant value of I note constant value of V. Then switch off the heater and record the final temperature, which I will call T final. Remember, we need the change in temperature, so it means delta theta is going to be the difference in the temperature, maybe T final minus T initial. So if we assume that there is no heat loss to the surrounding, if we assume no heat loss because of the insulation, we assume no heat loss to the surrounding, the amount of heat supplied, which I will call ES or QS normally, is going to be the amount of heat which goes into raising the temperature of the substance. That is, the amount of heat supplied will go into raising the temperature of the substance, that is mc delta theta. But which amount of heat is supplied? This is given by power times time, because energy is power times time. And power times time, because we have a steady current and we have a steady voltage, so the power will be I times V times T. So this will be equal to MC times the change in temperature, which will be T final minus T initial. So if only one set of values can are obtained, then I can verify or obtain specific T capacity to be equal to IVT divided by M into T final minus T initial. So that will be the specific heat capacity. Specific heat capacity will be therefore obtained by that simple method. You all needed is to look at the expression. You need to find the amount of heat supplied, which is going to cause a change in temperature. So you need the initial temperature before switching on the heater. Then now switch on the heater and note a steady value of current and voltage. These ones will help us tell the power of the heater. After a certain time, which is noted as T, then you can tell the energy supplied, which is power times time. So note the final temperature T final from the thermometer and obtain the specific capacity from that expression. So I think that one is very, very easy. Such descriptions, you will not find them in the exams, but the calculations will require a background knowledge. That's why I'm bringing these methods. Number two, how do we find or determine the specific capacity of a liquid? So still, the circuit is almost the same, only the nature of the heater is most likely going to be different or slightly different. So it's almost the same method, because you can see we have a power supply, we have a thermometer, only that we have now a liquid. We have an insulation to minimize heat losses to the surrounding. So this is quite different from the one that we have just seen for a solid, because for a solid, you could simply place the solid on a balance to find its mass. But here, you cannot just directly pour the liquid on the balance to find its mass. So one, we need to measure the liquid. We need to find the mass of the liquid using whatever method possible. Perhaps measure the mass of the empty container. Normally it is a calorimeter. Pour there the liquid, get the new mass of the liquid and the container, subtract to get the mass of the liquid. So one, we need the mass of the liquid. I'm calling it M. M is the mass of the liquid, whose specific capacity we are going to find. So number two, normally we stir the liquid so that there is thermal equilibrium within the liquid. So you stir the liquid and note its initial temperature, Ti. I will call it Ti initial temperature before switching on the heater. So stir the liquid. We normally stir the liquid so that thermal equilibrium is achieved throughout the liquid, because different sections of the liquid are most likely going to have different temperatures. So stir the liquid so that thermal equilibrium is attained, and record the initial temperature of the liquid, Ti. Then now we can insert our heater, insert the electrical heater, and maybe start your stopwatch. So now we can record the steady readings of the ammeter, that is I, and the voltmeter, that is V. These two are going to help us to find the power of the heater. So power is going to be I times V. So after a certain time T, we can now switch off. We can now switch off the heater, then stir the liquid again and note the final temperature Tf. So this means we can now get the difference in temperature delta theta as T final minus T initial. Then we also have the energy supplied. This will be the power times time, which is going to be equal to I Vt as the energy supplied. So if there is no loss of energy, we assume that there is no loss in energy or no energy loss with the surroundings, since we have added some insulation, then the energy supplied should go into raising the temperature of the liquid. Therefore, Qs should be equal to mc delta theta, but Qs is IV times T, should be equal to mc into change in temperature. So this will be T final minus T initial, close the brackets, which makes specific heat capacity to be IVT divided by M into T final minus T initial. So this will be a specific heat capacity. Is not very different from the previous one. So note, here we have also assumed that there is no heat loss to the surrounding, but this is a poor assumption. In practice, we can't avoid heat losses to the surrounding. If there were heat losses, then this equation here would be written as IVT equals to MC into T final minus T initial plus some of this heat going to the surrounding. Because when we heat the liquid, or by the way, we can even say plus or minus H, because the liquid could absorb energy from the surrounding, or there's a possibility that energy leaves the liquid to the surrounding. So I say plus or minus H, where H is going to be the amount of heat loss to the surrounding. So this is heat loss to the surrounding. So if thermal insulation cannot be relied on, that heat loss to the surrounding is not avoidable, then we can always write IVT equals into that plus or minus H, where normally H is used to represent thermal exchange with the surrounding, or the amount of heat exchanged with or absorbed or lost to the surrounding. So I think that one is very important. We shall see how we use H later on in the calculations. Okay, next, a better method can be thought of, and this is the continuous flow method. To determine the specific heat capacity of a liquid, I think the best method is the continuous flow method. It is a more reliable method for a liquid, and this could be actually demonstrated as we can see here in this slide. So instead of just placing a liquid in a calorimeter or in a container, measuring its initial temperature and final temperature, we can pass a liquid over a heater, as shown here in the diagram. It is called continuous flow because the liquid is meant to continuously flow over what? Over a heater. We are going to see that this method is better because it caters for heat exchange with the surrounding. So the liquid flows over a heater at a constant rate. That is, the same amount of the liquid per unit time flows over the heater. When the input temperature is Ti, so let's say the liquid enters from this point here, let the temperature with which it enters be measured as Ti from this thermometer here. And the output temperature, let's call the temperature with which the liquid leaves this side as measured with this thermometer is T0. So when the input temperature Ti and output temperature T0 are kept constant, these are noted together with the voltmeter readings, say V1, and the ammeter readings I1, and the mass of the liquid M1 collected, say, in a time of 5 minutes, that's around 300 seconds. So we can collect a certain mass, call it M1, coming out of this or coming out of this or running over the heater in a certain time. So we have the time, that is approximately 5 minutes. We have a fixed temperature T0 for the liquid coming out and a fixed temperature Ti for the liquid entering in, so that we have a constant difference in temperature between T0 and Ti. So the flow rate and the electrical power can now be adjusted. So we are going to control the flow rate. Because we want to have the same temperature difference, delta theta is going to be equal to T0 minus Ti every time. If this is to be constant in the same time, then the amount of mass or the amount of water running over the heater in this time cannot be the same as before if the difference in temperature is to remain the same. That means when we adjust the electrical power or the flow rate and the electrical power, then we can easily maintain the change in temperature. So to begin with, initially, a certain amount of mass M1 runs over the heater in a given time T at a temperature, initial temperature T1 coming out with the temperature T2. So the thermal energy supplied, which I'll call Qs, remember, is going to be equal to some of it raises the temperature, so it is gained by the liquid. It is gained by the liquid. And part of it is lost to the surrounding. So part of it could be lost or gained from the surrounding, lost to the surrounding. So initially, the energy supplied is power. Remember, energy supplied is power times time. So the power is actually I1 V1 times T. We are thinking of the initial conditions. So initially, I1 V1 T is supplied to the water or to the heater. Part of it raises the temperature of the heater. So this will be M1 times the specific capacity times the temperature difference, which is T0 minus T1. But part of it is lost to the surroundings. So I will say plus or minus H. Let me just say plus H. So we adjust the electrical power. Of course, that's why I have a variable resistor. When we adjust this changes and that changes, that this also changes, that means the power supplied has changed. So let's say now we have a new value of current I2, a new value of voltage V2, but we want it in the same time t. So it means if we are to maintain the same temperature change T0 minus T1, then the amount of the mass flowing over the heater must change. That is, the rate of flow must also change. So here we have a different mass M2, but the specific capacity is the same for the same substance. So this will still be plus H. So now we have two equations. Therefore, here we don't need to mind about thermal losses to the surrounding. By repeating for different values of M, I am eliminating thermal energy losses to the surrounding. Because when I subtract these two equations, H disappears. When I subtract these two equations, H disappears. So this is considered to be the best method for determining specific heat capacity of a liquid, because repeating the experiment for different values of mass cancels out energy exchange with the surrounding. Repeating the experiment for different values of mass or for different flow rate cancels out energy exchange or heat loss to the surrounding. So for the first set of values, I obtain that. When the power rating is adjusted, I obtain a different value. But remember, I always want to ensure that the temperature difference between the input and output are the same. Therefore, when I adjust this, I have changed the power, and yet the temperature is supposed to be the same, then the rate of flow should be changed. That is, the mass flowing over the heater should therefore be either increased or decreased depending on the power rating. Therefore, I am saying the continuous flow method is the best method for determining the specific heat capacity of a liquid. Simply because the continuous flow method allows measurement or repeating the experiment for different values of mass. And we have seen that repeating the experiment for different values of mass or repeating the experiment for different flow rates cancels out energy exchange with the surrounding, cancels out heat exchanges with the surrounding. Examples. 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 Example number one. Example number one. Calculate the heat energy required to raise the temperature of 200 grams. Calculate the heat energy required to raise the temperature of 200 grams of gold of specific heat capacity. Calculate the temperature required, calculate the heat energy required to raise the temperature of 200 grams of gold of specific heat capacity, 130. These are very easy questions for us. Calculate the heat energy, so Q is equal to mc delta theta, and we want the temperature to raise by 1000. So it means delta theta is 1000. Whether you say degrees Celsius or Kelvin, remember a change in temperature on the Kelvin scale is the same as a change in temperature on the Kelvin scale. Change in temperature on the Kelvin scale is the same as change in temperature on the degrees Celsius scale. So you don't need to convert this to Kelvin because they said to raise the temperature by this. This is the change in temperature. You don't need to convert it to Kelvin. It is still either 1000 degrees Celsius or 1000 Kelvin because it is a change in temperature. So when the amount of heat, this will be the mass, which is 0.2 times specific heat capacity, 130 times 1000. And Pressing the calculator, 0.2 times 130 times 1000. So this is giving me a 2.6 times 10 power 4 joules. As simple as that. I am saying the rise in temperature is a change in temperature. If the change is given as 1000 degrees Celsius, you don't need to convert this to Kelvin because a change in temperature on the Kelvin scale is the same as a change in temperature on the degrees Celsius scale. Don't begin adding here plus 273. I hope I've made that very clear. Example number 2. Calculate the quantity of heat energy required to raise the temperature of a mass of 810 grams of aluminium from 20 degrees Celsius to 75 degrees Celsius. So this is initial temperature, this is the final temperature. The specific capacity is given, so that is very easy. Amount of heat is equal to mc delta theta. So this will be equal to the mass. The mass is 0.81. Specific capacity is 910. The change in temperature will be 75 minus 20. Note that here I don't add plus 273. If I want to add plus 273, this is the same as 0.81 times 910 times. So this is what I would do, 75 plus 273 minus 20 plus 273. Any mathematician sees that 273 cancels out, which takes you back to the same value. So this gives you, pressing your calculator, 75. So this gives us this as 4.1 times 10 power 4 joules as the amount of heat. That is a very simple example. Number 3, I hope it's there. Number 3 and 4. Why did I give many examples? This is not acceptable. Okay, number 3 and for example number 3, let's assume this is number 3 and this is number 4. Calculate the specific capacity or given that 0.2 megajoules of energy are required to raise the temperature of this by that. This is the change in temperature. So we want the specific heat capacity of water. So amount of heat supplied is equal to mass times specific heat capacity times change in temperature. We want C. C will be the amount of heat supplied divided by m delta theta. So we are having Q as 0.2 times 10 power 6 because it's given in megajoules, divided by the mass is 0.6 because it's given in grams. The temperature change is 80. So we press our calculator. This is number 3. 0.2 exponent 6 divided by 80 times 0.6. Okay, so this is giving me, or it is giving us 4.2 times 10 power 2. 1, 2. So times 10 power 2, or approximately 4,200 joules per kilogram per Kelvin. So that will be the specific heat capacity. So that is the specific capacity of water. By the way, this value can also become part of it because it will appear many times. Specific capacity of water, 4,200 joules per kilogram per Kelvin, or it can be 4.2 joules per gram per Kelvin. Per gram, this is now per gram per Kelvin. So that is number 3. Number 4, an electric kettle rated 2 kilowatts is filled with water is filled with 2.0 kilograms of water and heated from 20 degrees Celsius to 90 degrees Celsius. Calculate the time taken to heat the water, assuming that all the electrical energy is used to heat the water in the plastic kettle, and the kettle has negligible heat capacity. So the energy supplied, Q, is equal to mass times C times change in temperature. But remember, energy is power times time. So this is mass times C times change in temperature. So the time will simply be mass C change in temperature divided by the power. I'm simply substituting. The mass is 2 kilograms. The specific capacity, let us assume the specific capacity of water is now known as 4,200. The change in temperature is from 20 to 98, which is 78. We don't add here to 73 because a change in temperature on the Kelvin scale is the same as a change in temperature on the degree Celsius scale. Divide by the power, which is 2,000. Press the calculator. 2 times 4,200 times 78 divided by 2,000. So it means this is going to take 327.6 seconds. So that would be the time. That would be the time taken to heat the water, assuming that all the electrical energy is used to heat the water in the plastic kettle, and the kettle has negligible heat capacity. I think those are enough examples. We now qualify for a self-check. This is going to be self-check number 2. In self-check number 2, we may need this data. Where possible, you may use these values where not given in the question. If it is aluminium, you can use 880 as the specific capacity if it's not given that question. Copper, you can use that one. Lead, glass. Glass, you can use any value in this range, but I'm very sure this question will not exist. Ice, for water, which is approximately 4,200, even if you use 4,200, there's no problem. For seawater, you can even use 400. Note that the specific capacity of seawater is less than that of pure water. Ethanol, specific capacity is that. I think even for alcohol, it could be around the same. And naturally, when you find such questions, you can also refer to this table. So, using that table, you should be able to attempt the self-check on this page. You have 1, 2, 3, 4, 5, 6 questions to attempt in self-check 2. So self-check 2 has 2 questions, and I think this will be the end of this lesson 2. Calculate the energy which must be supplied to raise the temperature of 5 kilograms. From that is a simple questions. Which requires more energy, heating this or of lead by 30 Kelvin or heating that kilograms of copper by 5 Kelvin. A well-insulated 1.2 kilogram of block of iron is heated using 50 watts for that time, 4.0 minutes. The temperature of the block rises from 22 to 45. Find the experimental value of the specific heat capacity of iron. Calculate the heat gained or lost for the following temperature changes. Use the table above to obtain the specific capacity. The table is on the previous slide. 45 grams of copper heated from 10 degrees Celsius to 90 degrees Celsius. 1.3 grams at 0 degrees Celsius cooled to negative 15 degrees Celsius. When 26400 joules of energy is supplied to 2.0 kilogram of aluminium, its temperature rises from 20 degrees Celsius to 35 degrees Celsius. The block is well insulated so that there is no energy loss to the surroundings. Determine the specific heat capacity of aluminium. A certain liquid has specific capacity. Remember, this is joules per gram per Kelvin. how much heat must be supplied to raise the temperature of water of 10 grams of the liquid from 20 degrees Celsius to 50 degrees Celsius. So that will be your self-check too. Remember to attempt that self-check and submit it together with um, submit your self-check together with your short summary. A summary is an outline of the most important points you have noted in that lesson. Thank you for watching. Watch out for lesson 2 and have a beautiful evening. Bye bye for now.